Okay, so in this video, we're going to take some Python code suggested by Davis Edwards for estimating Black-Scholes model, and we follow Espen Hoag's approach of a generalized Black-Scholes, where using the same parameter inputs, we can either output Merton or Black 1976. So just to see the approach here, we might just initially copy the code, implement in an online compiler, just basically because it's quite straightforward, and investigate our results. So we'll copy. Note here that the parameters here are simplified. So we have, for the Black 1976, we're going to start with parameters of 100 for the futures price, 100 for the exercise, T equal to 1 year, so maturity equal to 1 year, risk-free rate 5%, and the volatility is 20. And we'll go into online GBD, and we can remove this code here, select Python 3, we will paste. And when we run this now, we have to print our output. Right, so if we run as is, it will compile, but we won't get a result that we can observe. So we have to print, and let's just go back. We have to print C. Okay, so somehow, let's take both again down here, copy. Go into our online compiler, and we should paste, and then remove the pound sign to activate, and we want to print C. Okay, so let's run that, and this time we should get output including the Greeks, because we have a set of formula here for the Greeks. Right, so the value here is 7577. Okay, and then consistent with the chronology of the formula here, we get delta, so the value of the option for the call, the delta of the call, the gamma of the call, the theta of the call, the vega, and then finally we get the rho. Okay, so we can put in other values. In this case, let's take values we've been using to date, so 127.09, exercise 110, the time period is 1 year, the risk-free rate is equal to 10%, and the volatility is 8. Okay, so these are values we had used before in Excel. Let's copy and paste again. Right, paste, and let's execute, and we'll run again. Okay, and it has to go to the server. We have some output here, 1558, and we have these values for delta, gamma, theta, vega, and rho. Okay, so let's copy those, and now we'll go into a spreadsheet where we use these parameter values before, and we can compare against the estimates that we had run in the spreadsheet. So we had these values, that's here, and again the parameters 127.09, 110 exercise, risk-free rate 10%, time period or maturity 1 year for this option, and then a volatility of the return of 8. And okay, so let's paste, home, paste, and let's pause for a second. Okay, and what I we changed the font color here from being white to being black. Okay, so we get the output of 1558, which is consistent with for the call. And then for the using these parameters as given before, and then delta 08755, so that's consistent. The gamma is 0065, 00647. Vega for the option is consistent, 83611. We have Vega here, 835, slightly different. Let's check theta. Theta is equal to for the call option 122, that's the same as here. And then the row 9567, 9567. Okay, so the estimates are consistent. The only small difference I detect here is the 8354 as opposed to 8.36. That's a small difference. I'm not sure why. Okay, so one explanation why we may have a discrepancy here relates to the way we estimated the forward price. Previously, the forward price was B minus I to the power of R times the time period. That's 127.09, but it's a rounded figure. If we put in 127, 127.09 and return, there will be a small difference. But now the values for delta, the manually estimated values, are consistent with the values we have obtained here. So the output from Python, the 155841, is consistent with here from our VBA, and also the delta value 8754 is the same. The value for gamma 00647 is the same. The value for Vega 83611, 83611. The value for theta, the 1.2239 is the same, and the value for rho. Okay, so the Python code that we used is consistent. The output we get from this Python code is consistent with the formulae, the VBA output that we had obtained before. So this Python code looks to be in line with the previous values that we had used before.